Okay, today's plan, I would like to finish recursion just up to some point, and then we can talk about some new topics. And first of all, I would like to summarize what we have done so far. Okay, so this is a table. Don't be too scared. I will show you how you can find this table. It's actually quite important for you to review when you study for recursion. If you go to the lectures page and then scroll down until recently, and then you will see there is a required reading over there. Okay, you can see solving problems recursively. Okay, it's not very long. Just basically, it simply summarizes all the problems that we try to solve so far. So factorial, Fibonacci number, and etc. Right? When you go to the documents over there, it try to summarize for you how each problem can be solved by using the pattern. Right? We actually break down the bigger problem into strictly smaller problems and try to combine the solution to smaller problems together. Okay, so what I want to draw your attention for now is there is a table there, over there. Okay, you can rotate it when you study that. That one summarizes all the problems we're going to talk about in the class. Okay, I'm going to talk about some of them in the table, and then the rest will be up to you. Okay, again, just make sure you know how to get to the table from there. Okay, what I would like to do now is to go over a few, just to get some idea. Okay. Basically, whenever you try to solve recursive problems, you always want to have several things in mind. Okay, I'll show you. First of all, what is the problem? So far, the problems that we talk about, we have factorial, and then you simply given some input n. Okay. We also talk about Fibonacci number in the sequence, and also which one are you talking about, starting from 1, 2, or 3, right, and etc. Also, given a string, rather than number, you want to know whether there's a palindrome or not. I just say it's P for short. And also, given a string, you want to see what's the reverse of the string. And also, given a string, given a character, you want to calculate how many times the character occur in the string, right? And these are what we have solved so far. And today, we're going to look at two more. Okay, that's what we're going to do today, but the pattern will be similar. Let me just show you how you can read this particular table. Okay. It's a little bit mathematical, but don't be too terrified. It's not difficult. All you want to think about, first of all, are the base cases. For the case of the factorial, you want to say P0. Okay, the subscript 0 simply means the input of size 0. That means it can be solved trivially. P0 is simply factorial 0 will just be 1. And for the case of Fibonacci number, Fibonacci of 1, Fibonacci of 2, they are trivial. They can be solved right away. That's why they are base cases. And similarly, if you got its palindrome, the base cases will be empty string and also a single character, for which you got direct answer right away, and etc. So far, so good? Okay, that's how you read the table. And what you really want to pay attention to are the last two columns for the table. Okay? I'm going to give you one example. The third column there says recursive solution to subproblems. So subproblems simply means strictly smaller problem. For example, how do I solve P of n in the case of factorial? What I would do is I'm going to calculate P n minus 1, right? So that's something I simply assume that's going to be there. I don't have to calculate directly. Okay? Similarly, in the case of Fibonacci number, let's say if I want to calculate Fibonacci of n, what can I assume? I can assume I got Fibonacci n minus 1, which is strictly smaller, and also Fibonacci n minus 2, which is also strictly smaller. Let's do one more. What about its palindrome? Now let's say I want to calculate its palindrome of some string. The string might be very long for me to consider right away. What I will do is I'll take the middle part, which is a substring. So what you will see over there is I simply say P n minus 2. N minus 2 simply means I take out the first, I take out the last. So the middle string is of length minus 2 from the original string, right? In that case, I will say it's palindrome, and then this is the middle part of the string, okay? So this is middle part. Okay, that's how you read this particular column. So this column tells you how you can consider strictly smaller problem or problems, can be more than one. The final column here is really important. Given that we got base cases and given that we got something we can assume that's already available to us, the final thing is a solution. Okay? So now, how can we calculate the final solution for factorial, for example? This Pn minus 1, so this is the solution to a smaller problem, which you will assume. that is available. And then we simply say, whatever n it is, multiplied by this solution, that's what we get. So this solution column tells you how we can combine the various subproblem solutions together to get ultimate one. And what about Fibonacci? If I want to calculate Fibonacci of n, what I can do is calculate Fibonacci n minus 1, Fibonacci n minus 2, assume that they are there, and then combine them using addition. Okay? This table is very important for you to get an idea how to define recursive problems. Okay, I'll leave that to you. Okay? Basically, everything has been mentioned, but I put everything into a single table for you to look at. Okay? If you got any problem of reading it, let me know. Okay? I think that's valuable to you for you study. Any question, first of all, of the things we talked about so far? So far, we talked about, I think maybe the most complicated one would be the reverse of string or its palindrome, right? In some way, you're talking about an array of characters when you talk about string. What I would like to do, I want to do 2 more examples for recursion for today. The problems I want to talk about would be, let's say, given an array of integers, how can you see recursively if all the numbers in the array are positive? That's problem number 1. Problem number 2, how can you recursively determine if the array is sorted somehow? Okay? Both problems can be done iteratively using the loop, but let's say we want to force you to think recursively, let's say. Okay? Let's see what the problems are. Okay. Okay, just make sure you download the documents and make sure you study for that. That will also help you for the next lab number 5 later. Okay, so before I talk about the 2 problems, I would like to just draw your attention to the convention we're going to follow. Okay, you will actually follow the same convention for your lab number 5, so you get more practice. So the problem is, let's say you were given an array. Okay, so you can see so far the problem to solve is simply given an integer array A. Okay, A can be of size 10, A can be of size 0, can be anything, right? So now let's say this is the problem now we want to solve recursively. Okay? And every time you want to solve a problem recursively, you want to think about every time I want to make a recursive call, how can I make the problem strictly smaller? Okay? What we discussed last time, the naive way, is to simply, let's say this. If I got, let me turn to the iPad directly. Okay? Let's say this. If you have an array, A, B, C, D, okay, conceptually, I want to solve n, that's a problem I'm trying to solve, okay? And then, let me just write it, it's not exactly valid Java, but conceptually that will make sense. I want to have A, B, C, and then D. This is an array of size 4. Index 0, index 1, index 2, index 3. Let's say this problem initially is so big, I cannot solve it right away. When I make a recursive call, how can I make a strictly smaller problem? The naive way, but very inefficient, space-wise, is to say I simply try to run a loop. I create a new subarray over here. So let me show you. In this case, A, B, C, D is too large. So what I will do is I'm going to create a subarray. And the subarray is going to be starting from index 1, which means I ignore the first one, right? The subarray. So that would be simply B, C, and D. And the way to do it is by using a for loop. So it's very similar to how you did a birthday book example. Very similar. Okay? So now that means when you try to make the first recursive call, you're going to say n of this particular array. Okay? Now, B, C, and D, an array of size 3, is still way too large for me to consider. So what does that mean? That means I still have to execute this particular for loop the second time. So that means I'm going to try to create just another subarray. Subarray, and then, so now this time starting from index 1, which means I ignore the first one, right? So that means I'm going to get C and D. And then try to make a recursive call n of this array. You can see now the original array has been copied, somehow been duplicated for 2 times already, even for smaller cases. Okay, let's do one more. And then you can see that this guy here, CD, is still too large. So we only consider an array as trivial to solve when it's either empty or of size 1, either way. So in that case, we are going to create just another subarray by following this loop. So starting from 1 until the last index. So that means another subarray, which is going to point to just D, and then make a recursive call. And now this is of size 1, so now we can return. Consider this very naive, although it might work, solution. What's going to happen is when the array size gets very big, let's say 1,000. So that means on the way to making recursive calls, you have to duplicate the same array for 999 times. So that's very space wasting. So that's not the way to go. Okay? That's basically where we said about before the weekend last week. Okay? Any question about this? Okay? This way you should never do. Okay? Never try to do this. Okay? That's very inefficient because you got to keep duplicating the array. So now, a much more clever way to do it would be, we only specify what range of the elements in the array you want to consider for each recursive call. That's basically what we're going to focus on for this particular pattern. Okay? Let me show you very quickly. Okay? Similar idea, if I switch to here. Okay? Now, basically, we are still trying to solve the problem M still. M over here. And now let's go over the lines. Basically, the 3 lines over here are pretty much what you have to write about 70% or 60% of every problem you're going to solve. Okay? First of all, we simply say, okay, notice one thing. We got 2 extra parameters from index and also to index over here. Okay? 2 indices. Conceptually, let's say, for example, if we have an array over here, I'll draw that first of all. A is 0, 1, 2, and 3 of size 4. Okay? Now, we are not going to duplicate the array anymore. We do 2 things. Number 1, call by value. Remember call by value? You simply pass the address of the same array without creating any new array objects, number 1. And then number 2, you can think about, this is what we're trying to do. If you think about the array indices, let's say from and to. So these are the 2 indices, right? From and to. Initially, we're going to say from 0 until 3. That means we're going to consider this particular subarray, which means the whole thing. Okay? What about the first recursive call? What we will do, typically, is to increment the value of from by 1. So now from 1 to 3. We haven't created any new array. And then, so that means 1 to 3. Conceptually, we are considering this part of the array only. Okay? What about the next recursive call? You try to increment from again. So what you will do is you will try, let me use red. Okay? It's going to be incremented from 1 to 2, 2 to 3. And then 2 to 3 is going to be this guy over here. So now you can see from and to are getting closer and closer. Let's do a last recursive call. If you try to do another recursive call, how about green? So that means 3 and 3. So that means you're really considering 3 to 3, which is just a single element in the array. So this is a base case. That's where you can return, conceptually. Guys, do you see the difference between the 2? We're still at the conceptual level. Let me just say again, okay? We're almost done for the conceptual illustration, and then we can solve concrete problems. In the naive solution, you have to create so many arrays over here. Okay? That's a naive solution. In the more clever solution, we are simply introducing from and to over here, the indices. And then every time when you make a recursive call, you simply pass the from and to with some updates. What kind of updates do we do? You simply try to keep incrementing the from index between each recursive call. So you get closer and closer to the 2. Usually 2 will just be the last index of the array, just the last one, usually. Things get a little bit more complicated, and when you get more experience, you can change to 2 as well. But for now, you don't have to. Okay? And let me just show you one more. Oh, I think that'll be it. Okay? And when you do the exercise, okay, I got 3 examples over here that you can think about. Okay? But for now, I want to go directly to the problem so we can try to solve it. Okay? But any question conceptually about this? Basically, when I trace the recursive solution to the following 2 problems, I'm going to show you exactly how the from and to is going to change. So you'll see from will get closer and closer to the 2. Any questions? Yes? Sorry, say it again. I don't quite get your question. Yes. Oh, you mean over there? Yes. So the question was, if you look at the condition over here, the answer is, okay, let me just point it there. I see what your questions are. So guys, the question was over here. If you look at the base cases, this is base case number 1, when from is strictly larger than 2, right? Base case number 2, from is equal to 2, that's base case number 2. The reason I split them was because sometimes these two base cases may have to be handled separately. They might return different results. So in general, I will split them. However, in some specific cases, if both base cases will do the same thing, you can combine them. That's not a problem. Okay? Just now I'm presenting general case. Okay. All right, let's do problems concretely. Okay? Let me present the problem to you, and then I do have some conceptual problem to ask you about. Okay? Okay, that's about this slide here we just talked about, right? 2 examples here, naive versus clever. So now, this is our second last problem, okay, for recursion. Let's say we're given an array of integers. We want to know if all the numbers in the array are positive, okay? That's what we want to find out. Okay, let's just see how we can do it. First of all, I have a question for you. Always think about the simplest cases possible, okay? In the case of the collection or array, think about empty case, or also one single element case. If I have an empty array, should this method here return true or false? I'm given an empty array which contains no number. And I'm asking you, are all the numbers in this empty array positive? Should that be true or false? Well, I heard true, okay. Anybody who thought intuitively, don't worry about it. Don't worry about being wrong. Intuitively, if you think false, that's okay. But I would say let's think a little bit more logically. So 2 things I want to mention. For those of you who might be taking 1090 or 1019 at the same time, this is only for you. But you don't have to worry if you're not taking the course. Okay? Back in your 1019 or 1090 class, have you learned about this particular operator? For all, right? If I say for every x such that false, it is the case, some property of x. Do you know what that should be? Have you seen this? Maybe when you study about universal quantification. I'm saying that the false over here is the range. I'm saying for every x, such that x satisfy this particular range constraint. In this case, no x is going to satisfy false. False is always false. Now, I'm saying for every such x, I'm going to get p of x satisfied. The whole thing is going to be true. Okay? For those of you who is taking the course, I'm just reminding you, okay? If you're not, don't worry. Let me give you some intuition. This is how you can think about, okay? So let me just repeat the question over here. Are all the numbers in an empty array? Okay, let me just highlight it. Empty array, positive. Okay, one way to think about this is it possible to find a witness in empty array? Can I just say in, let me just call it A. Okay, A is empty. Is it possible to find a witness in A such that it is not positive? Think about the logic here. It's a little bit detouring. I'm just saying the following. I'm asking you if all the numbers in the empty array are positive. One way to think about is if you can find out any number that's going to violate being positive property, that means it's not all the numbers are positive. Can you find a number such that it's not positive? No, there's no number for you to find out from the empty array anyway. So that means there's no way to violate this property. So in the empty array, all numbers, if any, should be positive. Yes?
It's kind of the J-unit logic.
Yeah.
If it's not false, it's
yeah. Yes.
J-unit is pass.
Yeah, I can see what you mean. What Stefan was trying to say is, think about in the case of J-unit test method. You run the test method. If there's anything that goes wrong, so that means you should not pass. If you cannot find any line of code that's going to fail the test, that means you're going to pass. That's another way to think of it. Interesting. I haven't thought about that way. Okay, guys, anyway, don't be too bothered by the mathematical formula at the front. Okay, it's not covered by this course. I'm just saying, for those of you who are studying 1019, 1090, that's relevant. Okay, let me go back here. So now let's go back to this particular one. Okay, so that means now if I give you an empty array, if I'm asking whether all the numbers in the empty array are positive, the answer is true. Okay, because you cannot find any violation case for being positive. You just cannot. So that means it must be positive. Or let's say this, another example. Let's say for some reason, there's nobody registered for 2030. Let's say in winter 2020, let's say. The number of students registered in 2030 is simply 0. Nobody registered. Now, can I say everyone in 2030 actually pass? Yes, I can. Because I cannot find any students in that particular class, even though empty. I cannot find anybody in the class who actually failed the course. So that means everybody passed. Okay? This is a bit like a logical argument over there. Any questions? Yes? Yes, correct. So what you're saying is, let's change the method a little bit. Let's say we change, rather than all positive, let's say all negative. In that case, are all the numbers in the empty array negative? The answer is yes, because you cannot find any number that is not negative. Similar argument. Empty array is just a very special case you want to take care of. All right, so in this case, it's going to be true. Okay, that's a tricky case. So what about this guy here? Well, you can see all numbers there are positive, so that should be true. Okay. Now you can see there's a number there that's not positive. We can find a witness over there. So that means it should be false. Guys, any question about the examples here for all positive? You got to understand what the problem is first, and then we can handle the problem. Are we okay? Okay. If you're still struggling with the first empty array case, speak to me. Okay. In the worst case, if you're going to be tested this in the lab test, let's say, even if you just miss the empty case, the base case, it's not going to cost you to lose too many marks. Okay, but try to understand as much as you can. All right. So now, how can we solve this problem here recursively? Before I show you the code, okay, let me say this. Okay, let me get some idea over here. Interestingly, the way you try to solve a problem on array recursively is very similar to how you solve palindrome, and very similar to how you solve reverse of string. Very similar. You just have to somehow break down this array into subarrays somehow. Okay? Let me talk about conceptually first, and then we talk about how you can solve programmatically. Let's say this is your array A. Okay? Let's say we simply got 23, 46, let's say 4, and then minus, let me just give you something that will return true, and 99, okay? 0, 1, 2, and 3, so these are the indices, okay? So what's the problem? The problem is we want to know if all positive, and then we want to know A, okay? Let me just draw it. So this is what we want to know, but somehow the size of the problem is too big. We just cannot know. Okay, we cannot know right away. So this is how we can break down the problem. Conceptually, you can think about, we're going to break it down into two things. One is the first elements. Okay, the subproblem is going to be the remaining subarray, which is going to be drawn as green. So now let me write it down for you, and then you can think about it before we see the code. So we are basically saying A at index 0 must be positive for sure. And now this is where the recursion can occur. We simply say allPositive over here. Okay, let me write it conceptually. The subarray from index 1, okay, index 1 over here, to index, the last index, so a.length minus 1, which would be 3, because the size is 4. Index 3. So now, if you look at that over here, so this is basically how we can think about a strictly smaller subproblem over here. Okay, it's from index 1 to index 3, and this is strictly smaller. Okay, and we know that from the diagram, are all the numbers here positive? Yes. So that means this guy here is going to give us true. A0 is 23. 23 larger than 0 will give us true. So now what we can expect is that will give us true eventually. Okay? We haven't talked about recursive call just yet, but I wanted to show to you just the first level. Okay? Guys, any question? All I am asking you to understand from this slide here, number one, you should really understand that the original problem there, which is highlighted as blue, this guy here, which can contain all the elements in the array, is way too big for us to solve. In order to do it, what we will do is, number one, we're going to consider just the first elements. Number two, the remaining part is a subarray. Okay? And now the way we're going to do that is by using the from and to indices that we talked about. Okay? We're going to see that. Any questions before we move on to the solution, the programming solution? You okay? All right. Let's see the code very quickly. And then we're going to see how we can trace it. Maybe tracing it will give you more understanding. Okay, so base case will just be empty array. So that's exactly the argument I just talked about to give you intuition. Okay? The recursive case will be, you talk about the first elements and also the remaining part of the array. It's like making a recursive call. Okay, just some exercise for you. Okay, what if I want only some positive as opposed to all positive? Okay, that's something for you to think about. Okay, let's look at the code. What we'll do is this. First of all positive is going to take a single integer array and then returns a Boolean, right? Either true or false. Okay? And then this line is very critical. Okay? In order to implement a clever solution without being too naive and waste the space, what we will do is we're going to define the so-called recursive helper method. Okay? Which means in order to calculate all positive on an entire array, what we will do is we're going to make a helper method call. We're going to call the allPositive helper. It's a different method. We're going to see its definition in the following lines. And we're saying that call by value pass A directly over here. Call by value tells us we're only passing the address of the array without copying anything from the array. And then 0 over here is a from index. A.length minus 1. What's A.length minus 1 though? What is that conceptually? Last index, right? So we're saying to begin with, starting from index 0 until the last index. You're going to see that when we are trying to make a recursive call, in this allPositive helper, we're going to keep increasing from. Let's see what's going to happen. And now you're going to see something very familiar. So I say allPositive helper over here, you can see similar, but now we got from and to, right? Something we have seen. Okay, always try the two base cases. From larger than 2, so that means there's empty array. I'm going to show you an example. In that case, empty array will just be true, as we agree. Second base case, if from is equal to 2, for example, from maybe 4 to 4, right? That means I'm looking at the fifth elements in the array. In that case, I just want to know if that particular position, the element is larger than 0. Okay? And then finally, you can see this line is very important. The else part is making a recursive call. A at position from larger than 0, that's basically corresponding to this guy over here. Okay? This guy. Okay? Just in case you missed that. This guy here. And then when you see allPositive helper call by value, I'm not creating any new array. Simply say from plus 1. You can think about if from is simply starting with 0, from plus 1 will be 1. So that means I'm talking about from 1 until the last index. That's how I consider the subarray. Okay? Any question about syntax-wise? We haven't traced yet. Hopefully after tracing, you'll be even better. Okay? This pattern here may seem very odd in the beginning. You don't really see why do we create a helper method here. The reason, again, is because you don't want to create new arrays which will waste space across the recursive calls. We simply do call by value. We use the same array address, the same array objects. We just specify different indices range. That's what we're doing. Okay? Why don't we try to trace it quickly, just for the first one. Okay? And I'm going to trace with different inputs with you. Okay? Try to see if we can get all of them. Okay, that's basically the code that we just went through. Let's see the first case. Okay, so now start with something very simple. Let's assume we are trying to pass A. A is simply just empty array. Now, apparently, A now is going to be an empty array. Okay? So now that means A, you can think about A is pointing to some empty array over here. Okay? So now A here, when I try to make the recursive helper call, is going to pass the value of the address of A. Okay? 0, fine. What would be A.length minus 1? Well, A.length over here should be 0, right? It's empty array. So A.length over here is going to be 0. 0 minus 1 will give me minus 1. So that's why when you say all positive, where A is simply just empty, what you will get is calling the helper method here. I just say all positive helper for short. And 0 and minus 1. Okay? Are you okay up to now? Okay? So now we're now going to switch the context to the recursive helper method. Recursive helper method. Now we're going to go to this guy here, where from is simply 0 and 2 is minus 1. Are we going to make any recursive call? Well, we are simply reaching base cases. Base cases, right? Because now you can see from larger than 2. So now you can see from is 0, 2 is minus 1. 0 larger than minus 1, true. That means return true right away. So that's the simplest case you can get, but it works because we know that for the empty array, all the numbers there are positive. Okay, guys, are we okay with the first one? I think we are trying to gradually warm you up. Okay, second case. Let's make it slightly more complicated. Let's say A, the input is now going to be an array containing just one single element. Okay, so now we're going to make this call here. A will be called by value, and then 0, okay, always start with the first index. What would be A.length in this case? 1, right? Because only one element there. 1 minus 1 will be 0. So that means what you will do is, by passing this particular array with single element 4, what you will get is, you're going to get 0, and then the length minus 1, 0 and 0. Okay? Slightly different case than before. And then we are trying to execute this block of code for the recursive helper method. Are we going to reach the base case or recursive case? Base case, right? Because we got two base cases, remember? And back to your original question over there, why do we not combine the two if and else if statement together? It's because in the case of from larger than 2, it's always going to return true. But in the case of from equals 2, you may or may not return true, depending on what the first element is. So back to your question. Okay, so now we know that this one is not going to be satisfied. So now you got from and 2, 0 and 0. So that means you're going to return A from. What's A from? A0, which is 4. So that means 4 larger than 0 will give us true. That's not a problem. Any questions until now? We haven't seen any recursive case just yet. We're going to do one by one. Okay, you should be able to figure out if I try to change, let's say this. Let's say A is an array of size 1, but now I got minus 10. Okay, let's say this. If I do that, I'm going to make a recursive call, try to call the helper method, and now I still get 0 and 0. The size is the same. Okay, so now I'm still going to skip the first if statements, and then so now 0 equals 0 will be true. So that means what I will do is return A at position 0 larger than 0. Is minus 10 larger than 0? No. So that means when I try to do this particular one, it's going to give me false. Also correct. So it depends what the first element is. Okay, so base cases, always get them right first before you try to think about recursive case. Let's do the recursive case together. Okay. The same block of code, but now we consider a different array. Make it a little bit bigger. Okay. So what we have is we have an array A of size 4, 4, 7, 3, 9. Eventually, we know the result should be true, eventually. Okay, let's see if that's really going to be the case. Let's try that. So A the length over here for your information is simply just going to be 4. Okay, so now if you try that A call by value, first index 0, A the length minus 1, 3. That is why when you say all positive over here, where A is simply 4, 7, 3, and 9, it's going to end up calling this with 0 and 3. Okay, A the length minus 1. Okay, from index 0 to index 3. Okay, if you think about a little bit more, A pointing to 0, 1, 2, and 3. So these are the indices. And then I got 4, 7, 3, 9. So now let me do a little bit highlighting. Initially, when you say 0 and 3, so that means you're considering the entire array over here. Agree? Okay, in the beginning. Okay, so now if you think about this particular call over here, when I say all positive helper 0 and 3, okay, we know that none of the two base cases will be satisfied. Okay, that means we're going to say return A at position from. From is simply 0 at the moment, right? So that's why you get A 0 larger than 0 over here. And then we are trying to make a recursive call over here. And then from plus 1. So that would be 0 plus 1. And 2 remains to be 3. So that's why you see you see 1 and 3 over here. That means for this particular recursive call, we are considering, let me color that in blue. 1, 3 over here, we're considering this particular array over here. You can see no copy using loop is being done here. Question?
Maybe I missed something earlier, but just a question. Do we always have to go with like a smaller and smaller?
Yes, correct. Remember, every time you want to solve the problem recursively, you have to think about solving a strictly smaller problem, so you can combine the solution together. Yes. Okay. Yeah. Of course, a very naive mistake would be you say from plus 1, right, as opposed to from. Oh, sorry, say from minus 1. Yeah. Yeah. Okay, let's go a little bit further. Okay, for this one, I'm going to do very detailed with you. Okay, but just for you to get an idea. Okay, so now after this, what we will do is how do we handle this particular recursive call? Let's say this. So now we got 1 and 3, right? So now we got 1 and 3. Again, we're going to skip the if and else if. So now we're going to go for this particular return. A from over here is going to be 1, right? We got 1 here. And then all positive helper. So now we're going to give from plus 1, so 1 plus 1. And then 2 remains to be 3, right? So that means what we will get is, that's 2. So 2 and 3. So what we'll get is, let me use a highlighter here. So 2 and 3. Okay, so now that means we are considering this array. We haven't reached the base case just yet, not yet. We're getting there. And then, of course, for that particular call, don't forget A from is referring to A1. So that's why we say A1 larger than 0. Okay? Let's do one more. It seems like we are almost done. And then, how do we execute this particular 2 and 3, this recursive call? We're going to call that the final third time. We're not going to go into the base cases. So now we're going to execute this again, the third time. So now from is simply just 2. And then we're going to make a recursive call, right? A from. So that means we got A2 over here, okay? 2, and then we got A from, so A2, okay? How do we make this recursive call over here? So it's going to be from plus 1. So 2 plus 1, and then 2 remains to be 3. So that means we got 3 and 3 over here. Okay? And let me call it. Okay? 3 and 3. So that means we're considering just the last element over here. So now, are we reaching the base case? We are. Okay? If we have reached the base case, let's see how it can be resolved. So now it's 3 and 3. So now, when you try to call this a fourth time, which base case are we going to reach? The first one or the second one? The second one, right? Because it's 3 and 3. Okay? So now that means the purple one is going to go into from and 2. So that's going to be 3 and 3. So now A from larger than 0. So what this will end up executing will be A3 larger than 0. Now we are fine to return. So now notice something here. If you see that, what we end up evaluating will be A3 larger than 0 and A2 larger than 0, A1 larger than 0, and A0 larger than 0. There's something I didn't put in the tree, but let's put it now. The way you combine the result is by using the conjunction over here. So that means every time you try to make a recursive call, make sure it combine with conjunction. Okay, I just didn't put it. Okay. Okay, so now every element there is simply just positive. So eventually you will just get true. Okay? And if you look at what's really being evaluated implicitly is really how you did it with a loop. So they're equivalents. But the point about this exercise over here is to force you to think recursively. Okay? Guys, if you're okay with this, you're almost done for the recursion, at least for this point. Okay? Any questions, please? Okay, if no question here, let's now see the next one. Okay, this one, I'm not going to waste your time. I don't want to point out. This is the same block of code, but now I simply put -2 over here. Okay? And I want to speed up a little bit about tracing. What you will see is, since now the size of the array is still 4, that's the size of the array. So that's why you'll see 0, 3, and then 1, 3, 2, 3, and then 3, 3. Right? That's what you will see, how the indices change exactly like before. And then this will end up having A at position 3 larger than 0. That's the eventual one, right? And every one of them is going to be conjoined together, right? So now A3 larger than 0. Okay, let me just get rid of this. A3 larger than 0 is going to be true. A2 larger than 0 is going to be false. Right? And then A1 larger than 0 is going to be true. A0 larger than 0 is true. So eventually, because you got at least one false, the final result is false. Okay? The tracing pattern will be just identical as before. That's why I don't want to waste your time. Okay? But make sure you understand this. Question?
Is there a way to jump out once the first one is
You mean, you talk about short circuit, right?
Yeah.
Yes. So I think that for the tracing purpose, I want to show you everything here as if there was no short circuit. In the actual evaluation, I believe, since we talk about conjunction over here, as soon as we see this guy here is already false, there's no point to evaluate any further. I think that's what's going to happen at the runtime. But I think conceptually it doesn't hurt to see how the whole tree is going to look like. Yeah, good. Guys, any questions? Okay, good. How about I'll do one more exercise about recursion, okay? This pattern here is going to help you a lot, for the rest of the course, okay? Just make sure you can grasp the idea as much as you can, or talk to me. All right, let's see a final problem to solve about recursion for today. Is an array sorted, okay? So now, when I say non-descending, okay, there's some funny word in computer science you want to get used to. So now you will see very often, maybe in your 2011 or 3101, if I say an array is sorted in possibility A, ascending order, B, non-ascending order, C, descending order. I'm pretty sure you can predict what I'm going to write for D, right? Non-descending order. They meant something very similar, but not quite the same. For example, for those of you who already know the difference, what's the difference between A and B? Well, one is ascending, the other one is non-ascending. What's ascending really mean? That means the value is going to go strictly higher each time. For example, if the array looks like this, 1, 3, 4, and 5. This is a strictly ascending, right? 3 is larger than 1, 4 is larger than 3, 5 is larger than 4. Okay? What about this guy here? 1, 3, 3, 4, and 5. Is this ascending? Not really, right? It's not ascending because you can see it is not the case that 3 less than 3. That's not the case. Okay? So ascending over here basically tells you it must be a strictly less than between every adjacent elements in the array. Okay. What about non-ascending though? I agree with you that's greater than or equal to, but let's see what the derivation process is. Okay? Conceptually, you can think about ascending simply means less than. Non-ascending simply means not the case. Okay? If you think about logically, it's this symbol here if you're taking 1019 or 1090. Or in Java term, exclamation mark for negation. Okay? Non-ascending simply means it is not the case. For example, A0 is less than A1. For example, they are adjacent to each other. Okay? If it's not the case, so that means equivalent to A0 larger than or equal to A1. Not ascending simply means somehow it's decreasing somehow, but it can be also flat. Okay? Let me go a little bit like this. If you think about in terms of diagram over here, ascending is like this. You just go strictly higher each time. Okay? If you say non-ascending over here, that means you might go something like this, flat and go down. Okay? I will leave the descending. What's descending then? Well, strictly, right? Strictly less. So that means you go something like this. Okay? What about non-descending? Well, non-descending means it's not the case that A0 is strictly less than A1. So that's equivalent to A0 larger than or equal to A1. And non-descending is the case we're talking about right now. Right? Conceptually, if you want to draw a diagram, go something like this. You might go strictly increasing. You might stay flat for the next elements. You might go again and stay flat. Okay, so staying flat is allowed. You may have two adjacent elements who are the same. That's fine. Yes. Yes, absolutely. Sorry about that. I definitely agree. Because we talk about larger than or equal to. So you start with something here, go strictly down, may stay flat, go strictly down, stay flat, and go strictly down, stay flat.
So if it's not ascending, it's like the element before is less or equal to the element after.
Well, thank you. I think I got a fixed one here, right? Thank you. Let me write it down. Now, descending simply means I'm going down, right? So then it is not the case this. right? What's descending? Descending means I'm going downwards, and it is not the case. Agree? Yeah? Okay, let me just do it in a separate slide. So now we don't have agreement for non-descending. How about that? Non-descending. What is descending? Descending is, so that means, let's say A0, for example, must be greater than A1. Would you agree that's descending? That's a descending, right? So now we're saying not the case. Not the case. That should be equivalent to A0 less than or equal to A1. Agree? Good. So now let's redraw the diagram. Okay? If I redraw the diagram, it's going to be something like this. It's going to be smaller than or equal to. This one might stay flat, go strictly higher. Stay flat, go strictly higher. Yes. Now you're convinced. Yes. And everybody else convinced? The reason I want to put A, B, C, D all in one place is because you might get different case to solve. Okay? Make sure you're comfortable with the analogy. The none in B and D are simply means go take the negation of that. Okay? So you go from strictly less than into greater than or equal to, and vice versa. All right. Any question about this? Okay. So now after this, what I will do is I'll go back to this original problem here. So now let's talk about non-descending. Okay, you're still getting used to the terminology, so I'll tell you right away. Non-descending simply means you can go flat and then go up, flat and then go up. Okay. And now, empty array. All right, empty array is our friend because you always get the base cases defined on that. Should empty array be considered as sorted in non-descending order? Okay, so now if you say yes, try to apply the same argument as before. Because you cannot find any two adjacent elements in the empty array such that it is not sorted. You can find a violation, the same idea. Okay, so that will be true. Okay, so that will simply give you true here. And then what about 1, 2, 2, 3, 4? You got flat, right? So that's okay. So even though it's flat, that's fine. If I change the question a little bit to say ascending, in that case, that would be false in case. Okay, what about 1, 2, 2, 1, 3? False, right? Can you tell me which one is going to give me a witness of violation? From 2 to 1, agree? Right? You can see from 2 to 1, it's not either flat or strictly increasing, right? Increasing. Okay, so now we're going to basically see a very similar pattern as before, okay? Let me draw some visual hints for you. Okay, before I do that, why don't you take 30 seconds to think about how you might do this problem here. Basically, you're going to think about if I'm given an array that's too large to solve right away, how can I somehow divide that into a subarray? And how do I do the subarray? I can use index range, as I did before, right? Think about that issue here, okay? Think about. And while you are thinking about, I'll prepare something on iPad, and then we can go over that when you are done. Okay, so now let's think about it. Basically, this is what's going to end up happening, okay? The original problem here is the follows. We want to see if the entire array is sorted in non-descending order. That's the original problem. Too big for me to solve. What I would do is, I would say I will only consider the first element over here and its right neighbor. And then the recursive call is going to consider whether the remaining part of the array is sorted. So what's going to happen is, think about the first call. It's going to be sorted, okay, is sorted A, mathematically speaking, is equivalent to, so this is not a sign, just equal to, okay, is equivalent to First of all, A0 I'm considering right now is less than or equal to its neighbor. Okay? And the rest of the array is sorted. It's sorted, and then I'm going to say subarray from index 1 to index 4, right? Similar ideas before. From indices 1, 2, 4. So now the only challenge for you is to see how you can specify this pattern over here. But we learned about it in the previous example, right? Guys, any questions? Let's do that quickly, okay? If you see the code, let's see the code very quickly. All right, so now what you will see is, number one, you can see it's sorted with, I simply call the recursive helper method. So from 0 until the last index, same as before. And then I say it's sorted helper. So now, from larger than 2 means empty array. I return true, okay? If from is equal to 2, that means a single array, a single elements array. In this case, single element array is always sorted, right? There's no way to find violation in a single element array, just true. And then, if it is the recursive case, what we will do is from less than or equal to from plus 1. We're going to see exactly how this is going to work. And then call the helper method and then say from plus 1. Okay, the same as before. That's the code. You can see the coding itself is not so complicated, but tracing it to get insight, we definitely need to do together. Okay, as before, I will do several cases with you. Okay, just get you comfortable. Any question about the coding over here? Everybody's okay? All right. By the way, all the code, Java code has been made available to you. Feel free to play with it. Okay, you can download the code from the lecture's website. All right, let's do chunk tracing together. Okay, as before, let's try with the base case. Okay, that's the code. This. Okay, always start with something simple. Let's say we are considering A being empty. Well, wouldn't you agree? It's going to be called a recursive helper method. First index always 0. A.length minus 1 will be minus 1, right? Because the length of this array will be 0. 0 minus 1, minus 1. So that means we're going to get 0 larger than minus 1 will be true. So that means you simply just return true. Okay? The first base case is very easy, but make sure you get it right. Any questions about the first base case? Okay, let's see the second base case where you got a single element in the array. Slightly more complicated, slightly. So now you can see A will just be a single element array. A.length now will just be 1. 1 minus 1 will be 0. So that means you're going to call 0 and 0. And if you agree, we're going to see this particular branch, right? 0 equals 0. And we simply return true. Also turned out to be very simple. When the number of elements is simply 1, you just sort it automatically in either order. Okay? Return true. Okay? Let's see the more complicated case now, where we're going to have recursion. Before I trace specifically for this example, can you see the tree structure here is very similar to what we did before? Very similar, right? Specifically, let's see this. We started with 0, 3, and then we go to 1, 3, and then 2, 3, 3, 3. You can see the from index is always incremented by 1 until we get very close to the 2, so we can solve it right away. Okay? That's something to note first. Okay? And now what I want to do is give you a little bit more high-level tracing. Okay? Not as detailed as before, but let's see this. 3, 6, 6, 7. A is pointing to this guy here. 3, 6, 6, 7. And then the indices are simply 0, 1, 2, and 3. Okay, let's see how we can do it. So now when we say 0, 3 over here, so we are basically saying to begin with, we want to consider the entire array over here, right? And because over here, you can see just for the first one, this is the from. This is the 2. Okay, you can see for the recursive case, A from less than or equal to A from plus 1. So that means you're going to see So this is from, and this is from plus 1. That's why you see A0 less than or equal to A1, right? For the very first recursive call. Just make sure you're okay with it, okay? It's very important to see what the from and to are in each recursive call. Okay, after this, we're going to make another recursive call, and then we're going to say 1, 3. That means we're going to consider whether this particular subarray is sorted, right? And then after that, we're going to go into C over here, 2, 3. That means whether this particular subarray is sorted. Okay, we haven't reached the base case just yet, not yet. And then one more, what about yellow? And then 3, 3. So this is the last one to consider because now 3, 3 is going to reach this particular base case. Oh, sorry, not this one here. This guy here, right? So that means this particular recursive call is simply just going to return back to us true. Okay? And now if we go back to every recursive call, A2 less than or equal to A3 is true. A1 less than or equal to A2, A1 less than or equal to A2 is also true. A0 less than or equal to A1 is also true. So you get true and true and true and true, all the way true, using conjunction here. I'm doing a little bit fast because if I trace a bit more detail, you might just get lost. But hopefully this will give you the idea. What you really want to have in your mind is to see overall, we are trying to make this many recursive call. This guy here, 2, 3, and 4. Each one of them simply correspond to the subarray of this size, this size, this size, and this size. Right? Each time we're trying to make the subarray to be considered smaller, strictly smaller. That's really important. You good? Questions? Okay, so your lab number 5 is going to contain some exercises for you to strengthen the understanding. So maybe we can go over some of them in the class later, okay, if you got trouble. Any questions before I switch the topic? As far as your study is concerned, I believe I'm going to make it clearer for you when I release the Lab Test 2 guide later. But I would suggest, if you see the slides, trying to study until slide 24. Okay? After that, we talk about binary search, merge, sort. That's only for the end of the semester. For now, I think that's just enough for you to do Lab 5. Okay? Any questions? All right. Let's do something new. Okay? Recursion is actually quite a challenging topic. So for this course, we'll just give you a little bit touch of the subject. You're going to use that for later courses as well. Okay? But for now, let's go back to object orientation, which is a different concern for this course. So what I will do is, let me just switch to this new lecture slides, aggregation and composition. Okay? Hopefully we can finish this topic today and also Wednesday, so we can start inheritance from next week. Okay? Hopefully, that's the plan. Okay, aggregation composition. We just mainly just go by principle and then do some examples together. Okay, so now in order to see aggregation and composition, let's get some terminology straight quickly, okay, and then we'll go over examples. Okay, so now I want you to get familiar with these two terms, okay? One is called container, the other one is called containee, okay? These two, okay? Let me read off the definition to you, and then we'll see example. An object that contains others is a container. For example, array. You've got an array of points. The array itself is the container. Okay? Containee is an object that's being contained. For example, if you got an array of points, the array is a container. The point is a containee. It's being contained in the container. Okay? We just needed these two terms in order to show you the difference between aggregation and composition. Okay? And now let's see some wording over here. Let's see some example. Let's say each course has a faculty member as its instructor. So now, can you actually see who is the container? Let's say we got two classes over here. We got a course class, and also we got a faculty class. according to the definition above, do you think course is a container or faculty is a container? Well, since we say each course has a faculty, so they contain the faculty. Okay? Okay, so in this case, container is the course, containee is a faculty. So now, how do you visualize this at the runtime? Eventually, we have to turn this into Java code and it should be executed at the runtime. But how do you visualize that? Let's see a diagram over here. So here I'm saying course is a container, which means every course contains some containee, which is faculty. How do we see that? Let's say this. So this is kind of like a complicated object diagram, but I'll guide you through. Don't worry. Okay? Let's focus on what we need to know for now. So this diagram we use for many examples. Eventually get very familiar with it. Let's see this. First of all, can you just see we got two course objects over here. One is 2030, the other one is 3311. We simply got its title over here for the two courses, right? Two course objects. So now, when I say, let me just read the sentence to you again. When I say each course has a faculty member as its instructor, let's say the prof. So now you can see for this particular course for 2030, it has an attribute prof which contains the address of some faculty objects. So this is container over here, this is containee. Okay, similarly, you can see for software design course, it also has a prof which points to another faculty object. So this is container. You can think about this is container. And this guy here is containee. Question?
So we usually have like a lot of like things inside things like Russian SQLs kind of situation.
So say it again. You mean you have?
Like you have like some containers are containees as well.
Yes,
a lot of things
exactly. So in this simple case over here, in this case, you say course is a container. The course contains prof, being faculty. Absolutely right. Sometimes the container might be the containee with respect to another class. For example, let's see that right away. Okay, let me just be consistent with my color notation here. You can see for this particular pointer here, you can see it's pink, right? We got a container, containee. Okay, let's see another case over here right away. Can you see over here, we got the student class objects over here. Each student has an array of courses, I call it CS. And then over here contains an array of course references. In that case, the first course is referring to 2030. The second course is referring to 3311. So now you can see who is a container. The students, right? Because student contains a list of courses, right? So now as far as this green link is concerned, you can see this link over here, and also this link over here. As far as this one is concerned, you can see I have over here, this is a container. And this is a containee. So there's no absolute container always, it's relative. Okay? Guys, are we okay with this? Okay, somehow the structure should be very familiar with how you did it for the birthday book. It should be very similar. Okay? So hopefully that's okay for you. And as you pointed out, each class may be container and containee at the same time, depending on which link you're talking about. Depends. Okay? Okay. Having this in mind, let's go over a little bit more on the slides, and then we can go on with some concrete example. Okay? But this diagram, we're going to see that many times. Okay, so now each student is registered. Okay, exactly what I said. Containers will be student, faculty, and also containee. Okay. Okay, for these you're going to see exactly how this is going to work even later on. Okay. So now there is another kind of container and containee you have to be aware of. For example, let's say this. Let's say we have a file system. You know what a directory is? Like a folder, right? Let's say each folder contains several files. So that's why I got container and containee. Okay? But now what's the difference over here? The difference is, let me just show you very quickly. Okay? conceptually, what if a course is deleted? Let's say for some reason 2030 is not offered anymore. So we have to delete it, the objects from the runtime. How do we do that, right? Conceptually, this is what you will have to do. What you will do is you will simply just cross this object out, somehow assign the reference to null. That's basically what you will do in the birthday book. You simply get rid of it, just delete it, so the course doesn't exist anymore. However, when you are doing that, let's say Jim, he used to be registered in 2030. When you delete 2030, should you delete Jim as well? You shouldn't. So that means Jim can exist independently of the course. Actually, that would be very bad. Otherwise, if I just cancel 2030 now, all your student record will be canceled, right? That's not good. Okay? So this is something to note. Okay? We'll see more example later. On the other hand, let's see a different case. Let's say directory and file. The easiest one is to see the following. Let's see if you can look at my desktop over here. Let's say I got a directory called D, right? Under which I got F1, F2, F3. Okay? Very easy to see. If I delete D, does it delete all the files at the same time? It does. That's it. Just a different case, right? Don't worry, it's something unimportant, so I don't have to worry. Okay? I just created on the fly. Anyway, so we're going to see these two kinds of example where the containee may or may not exist together with the container. That's something you want to pay attention to. Okay? In the case where the containee can be independent from the container, is something called aggregation. Okay? On the other hand, when they have to coexist together, it's called composition. Okay? You just want to get used to the definition. Take some time. Okay? That's basically what this slide is talking about. So what I will do, I'll see how much example I can go over. I'll go over at least one. So now this is some diagram notation just for your knowledge. This is so-called UML diagram, but later on you're going to see much more similar stuff when you take the 3311, the software design course. But for this course, just give you a little bit introduction. Okay? Basically, let me just go over notation together with you. Okay? So now, let's see. Notice that there is a diamond over here, right? The way I remember this notation is like this. You can think about a diamond means contains. Okay? So when I draw the diamond on this course site, it simply means every course contains a single faculty as its prof. Okay, I'll write it down for you. Each course objects contains just a one, faculty objects as its prof. At the design level, that's what I'm trying to say. Okay? How do we implement that? You'll see that's very straightforward to implement this. What I should do is, in the course class over here, I simply declare a prof. You can see the prof over here correspond to the prof over here. Right? The prof of what type? Faculty. Okay? And as we learned before, if you declare an attribute of faculty type, that means it's going to store the address of some faculty objects, right? Okay. Okay, let's see the second one. Similar idea. Okay? I'll write it down for you just for completeness. As I said before, the diamond here simply means contains. So that means each student's objects contains. Now, when we say star, simply means one or more, or a collection of, one or more. Okay? Contains a collection of course objects as their, okay, since we talk about student, right? courses. Okay, that's how you interpret that. So now how do we implement that? Very straightforward. Because you can see that when we got a student class over here, we simply say you got courses, you can see the courses over here correspond to the courses over here, right? Just have the matching attributes. And then it should be, for example, array type, right? That's something you're very familiar with. So later on in future courses, you may not necessarily always start with the code. You don't. You may want to start with a diagram as your design before you move on to the code. Okay? That's something you will see beyond this course. Okay, but I do expect to read the basic about the diagram. No, as much as I have said. Any questions? Okay, we're going to consider these cases all together. We're going to see at the runtime how objects or how multiple classes can work together. And that means we've got aliasing. And also we have to navigate between the classes. That's the key. Okay? So what I will do is, let me see. I got about 3 minutes, 4 minutes. Okay, let's see what we should have. Okay. Let me just introduce to you the class, first of all. Okay, and then we'll move on to the examples quickly on Wednesday. Let's say we have a course class over here. Each course has title. They also has a prof. You can see over here, the prof over here corresponds to this particular aggregation, right? So every course contains, you can see the diamond here, contains a single one prof, faculty as their prof, right? And then we have course constructor here, which will initialize the course objects. And then we got set prof, set a particular prof to be the instructor for this course, okay? And then also get a prof. Let's say you have second class. And then we got a faculty class here. We got a name. And also we got to initialize the faculty with a name, Jonathan, Jackie, etc. And then we can set a name for the faculty. And then get a name. Very easy 2 classes, very easy, okay? What I will do is, since we got very limited time, so I just want to take 1 more minute. I'll let you go earlier today, okay? I want you to look at very quickly the test code we want to have, and then to see what's going on. Picture in your mind what's going to happen, okay? A little bit exercise for you if you want to practice drawing some diagram. We're going to draw lots of diagrams on Wednesday, okay? Let's say this is what's going to happen, right? We're going to see create 2 course objects, first of all. And then create a faculty object, let's say myself, and then we set myself to be 2030 and 3311 instructor, okay? Because you're very close to what you consider in your real life. After this, we're going to say, make sure the professor for both courses refer to the same objects. Should this be pass or fail? Okay, think about it. Okay, you don't have to answer me now. Think about it. And then, let's say, if I say set the name of the prof from Jackie to Jeff. So now, if I try to see if these two still refer to the same prof, do they refer to the same prof, first of all? And what about the name? Should it be still Jackie or Jeff? Well, depends which course you're talking about, right? That's kind of the issue. And then finally, let's say we create another faculty object called Jonathan, right? And then we set the instructor for 3311 to be Jonathan. And then try to see if the instructor are now referred to the same object or not, okay? And etc. Okay, that's something we'll start with on Wednesday. Okay, try to see if we can picture what's going to happen. Okay, I'll see you on Wednesday.